is a graded set. Boy, that's a mess. No? Yeah, graded set 2, the solutions to homework set 2, and homework set 4. Now the solutions to 2 in homework set 4 will be available on the website. The graded homework, if you don't pick it up here, will be in the bin on the second floor of the Packard building, roughly in the middle. The bin labeled EE 376A. Now, let me remind you of the schedule. Next Tuesday will be a double lecture. It'll go from 11 till 1. There'll be a break in the middle. On Thursday will be a double lecture. It'll go from 11 until 1. There'll be a break in the middle. Those lectures will cover all of chapters 5 and 6. 5 and 6 on gambling, Kelly gambling, and data compression, Huffman coding, the optimality of Huffman coding, and everything you need to know. Then there'll be a week where we don't have classes. That's Tuesday and Thursday. Not next week, but the week thereafter. Then when we come back, we'll start lectures on channel capacity, which will take us through, we'll go through channel capacity and the capacity of the Gaussian channel through to the end of the quarter. There will be a midterm on Thursday, February 17th. Again, we'll put this up on the website. And that will be after the first lecture on channel capacity. But the midterm will only cover chapters 1 through 6. Okay. All right. All right, last time, any questions on the structure as we go on? All right. The end of the course, end of this quarter, will, as I mentioned, will be on the 2 chapters having to do with channel capacity, both the proof of the theorem and the converse, and the application to the Gaussian channel, which gives you the most famous formula in information theory. The channel capacity is the bandwidth times log of 1 plus the signal-to-noise ratio, the power over NW, where W is the bandwidth and N is the noise spectral density in that bandwidth. Okay. Last time, we looked at the second law, and today, after making a couple of summary statements about the second law, we will prove that for Markov chains, that the distribution at time n, when you start in a non-equilibrium state, converges monotonically to the stationary distribution. Again, just showing the naturalness of the algebra of information that we're dealing with. Things are monotonic when they should be, and so on. And then we will look at optimum gambling. On horse race stock markets. And that's chapter 6. And we'll prove, among other things, I hope today, that the entropy of a horse race plus the doubling rate, the rate at which you can double your money, the exponent, is a constant equal to the number of horses under mild assumptions. So every bit of randomness that you lost increases your money by a factor of 2. That is, gives you 1 bit in the doubling rate. All right, the summary from the second law last time is that the entropy of the present given the past is always, for all processes, increasing, and that's because if this is 0 and this is minus n, as the past recedes, you have less information. All right, and then the entropy, something that looks much like this, xn, given the past up through the present, increases not for every process, but for stationary processes. And the reason is, if it isn't stationary, something being n units in the future, with stationarity, we just subtract n from each. We shift everything in and we get this. And then we throw information away. But an example, counterexample to this always being true is let the x sub I be IID and let the entropy of x sub I be bounce around. So this could be then bouncing around. Here there's no bouncing around because it's always x0. And then the question is, when is the entropy of xn given just the observation at the present time, not the entire infinite history? That increases, and that increases for stationary Markov. So if it's stationary and Markov, then you have this stronger statement. And this is always true. H of x given x naught is concave. Also for stationary Markov. And finally, our final statement was the future from n to infinity, and the past from minus infinity to 0 is decreasing and convex. For all stationary, no Markov needed, because really, if you think of it, the infinite past acts as a Markov state. And the general idea useful information degrades. This is the information equivalent of the second law. The second law says useful energy becomes useless. This theorem states that the useful information becomes less useful. Now, we believe the current feeling in physics is that information is preserved. When you throw things into black holes, it gets radiated out over the next several billion years, and it looks essentially like black body radiation. But in it is information about what was swallowed up in the hole. So you don't ever lose information in the universe. It just becomes more and more microscopically, homogeneously distributed and becomes impossible to measure because you measure macroscopically. And another summary of this statement is the distinguishability of the past given the present decreases as the past recedes. Or the predictability of the future is given the history up to now becomes less and less resolvable. By the way, some of this is nice if you just talk about mutual information. With the channel capacity theorems, we'll see it has a crisp statement. It's the log of the number of distinguishable states in the future. The nice thing about such a statement is you don't care which states you're distinguishing. These aren't code words from the past. There's that. For example, suppose you look at an image. What's the degree of resolution of your ability to inspect the image? Well, it has to do with how far you're standing away from it. It's blurry. You can't tell the difference between two letters on the eye chart if they're too small. That's roughly the notion of distinguishability. It's not the notion that you can't distinguish an E from a C. That's a specific way of making concrete the notion that you can't distinguish too finely. By the way, when Turing did his great work in 1936, proving the existence of universal Turing machines and the unsolvability of the halting problem, he essentially said, I'm going to build a computer, or talk about a computer, that models human thought. But when he did it, he said there's a finite alphabet that this computer deals with. Zeros and ones, or A's through Z's, and so on. But it's a finite alphabet, and his argument was there are only a finite number of resolvable symbols in a certain amount of space. So he was implicitly saying that's how resolvable things were. Also, he made it a finite state machine with unlimited tape. This corresponds to saying the number of resolvable states in the human brain are finite. Then he allowed an unbounded work tape. You know, when you solve a problem, you generate a lot of scratch paper and so on. And then you go to the next state of your thought about it. So, in that sense, it's not a finite state machine because you have access sort of to an infinite amount of memory that you can call and fill up. And then that allows you to do the computations that the Turing machine can do.